Chapter 6, Circular Motion and Other Applications of Newton's Laws. We introduced Newton's 3 laws in the previous chapter. In this chapter, we're going to study some further applications. In particular, we're going to focus on the circular motion. If an object moves in a circle, how does the dynamics of a circular motion work? When we apply Newton's second law to the circular motion, what happens? We'll look at examples of that. We're also going to look at a case where when you study the motion of an object from a reference frame that itself is accelerating, we call it accelerated frame of reference, then what happens? Okay, let's first study circular motion. We know from chapter 4 that when we study the kinematics of circular motion, and when an object moves in a circle, then it is certainly undergoing an acceleration. Let's review what we learned in chapter 4, the kinematics of circular motion. Suppose an object moves in a circle of radius r centered at point O. This is the velocity of the object at one moment. Of course, the velocity is tangential to the circle. The radius is perpendicular to the circle. Suppose we look at the acceleration. We know the acceleration in general can have two components. This is the acceleration. One component of the acceleration is along the direction of motion. Okay? That's that component. It's parallel or anti-parallel to the direction of motion. We call it aparallel. That's that component. That component. And there is another component that is perpendicular to the direction of motion. Okay? For that reason, we call it aperp. Aperp. So in general, any acceleration can always be decomposed to be a component along the direction of motion and a component perpendicular to the direction of motion. Now, what does this component accomplish? Well, in this particular case, when you move this way and this acceleration pushes you this way, which means you're going faster and faster. That means in this particular case, this parallel component increases the speed or increases the magnitude of the velocity. Okay? Now, in fact, if this aperp is anti-parallel to the velocity, then of course it's going to slow it down. So as a result, the speed decreases or the magnitude of velocity decreases. So this is what aparallel accomplishes. It changes the speed, okay, or the magnitude of the velocity. Changes the magnitude of the velocity. But you know, velocity is a vector, so we also got to change its direction when it does not move in a straight line. In particular, if something moves in a circle, then of course the direction of motion constantly changes, and that requires another acceleration. That acceleration does not speed up or slow down the motion. Rather, it just turns it around, it changes the direction of the velocity. And that is a component, the other component, that is, of the acceleration. It's perpendicular to the velocity. So it's neither pushing it or pulling it, rather it's just pull it to the side. It's called aperp. Since for circular motion, they're moving tangentially, right? So aperp is then radial. In fact, it's pointing toward the center of the circle, and we learned in chapter 4, what is that equal to? That equals to v squared over r, r being the radius of the circle. You recall that? Very good. And we had a name for it. We call it centripetal acceleration, C. Centripetal. Centripetal means center seeking. And we can also call it aperp because it's perpendicular to the direction of motion. So what does aperp do? It changes the direction of v, okay? So when you look at an object in circular motion, its speed may or may not be changed. In other words, aparallel may or may not exist. If it exists, then what you have is called non-uniform circular motion, which means the speed can increase or decrease. But regardless, as long as the object moves in a circle, you must have a aperp. In other words, you must have centripetal acceleration, because that's what it takes to turn around so that it can move in a circle. And the centripetal acceleration equals v squared over r. What we're going to do is we're going to apply the knowledge of the kinematic consideration, which is a centripetal equals v squared over r, to study the dynamics of circular motion. Okay, when we say F equals ma, right, that's the Newton's second law, and then in particular a equals v squared over r, the centripetal acceleration, then we get the dynamics of circular motion. Okay, so let's look at the dynamics of circular motion. Let us apply F equals ma. When an object moves in a circle, there has to be a centripetal acceleration perpendicular to the direction of motion. Whether or not it also has a component of the acceleration that's parallel to v, we don't know yet. But let's, for simplicity, assume for now that it's a uniform circular motion, which means the speed does not change. What does that tell you? It tells you that there is no component of the acceleration that's parallel to v or anti-parallel. The acceleration is entirely perpendicular to the velocity. That acceleration is responsible only changing the speed, direction of motion, but not the speed. Okay, for uniform circular motion. Okay, that is a special case that we study for now. So if it's a uniform circular motion, that means v does not change. Okay, so that tells us that a is perpendicular to v. We only have a perp, and that is that a here. It's also the centripetal acceleration, right? And that a, let's plug in here. What do I get? In order to supply the centripetal acceleration, somebody has to exert a centripetal force on this object that pulls it in towards the center of the circle. That centripetal force is responsible for the centripetal acceleration, MAC. So how much is that equal to? Well, that equals m times, let's plug in the value for AC. That is v squared over r. That is the magnitude. What are the direction? Well, the direction is from the object directly into the center of the circle. It is opposite to the vector pointing from the center of the circle out. Okay, now that vector pointing out, let me use a unit vector r to denote it. Then of course, since our force goes in, there is a negative sign in front of it. Okay, there is a negative sign. That negative sign tells you the actual force is inward, not outward. Okay, so that is the vector form of Newton's second law applied to uniform circular motion that has a constant speed, but it turns around so that you still need an acceleration, which is provided by the centripetal force. Okay, centripetal also means center seeking, as you remember. That means there has to be a force exerted on the object that pulls it toward the center of the circle. The scalar form is Fc equals m v squared over r. We're going to apply this formula in many different cases to study the dynamics of circular motion. Let's be clear about one thing. When we say centripetal force, that is a force provided by whatever means on the object that pulls it toward the center of the circle so that it can sustain a circular motion. This centripetal force can be provided by, for example, a string which has a tension. It can be provided by the gravitational force, can be provided by electrical force, whatever. Okay, but when we have a string, let's say we use a string to tie a stone, and then we turn the string around so that the stone does a circular motion, right? So in this case, it is the tension in the string that's pulling on the stone to make it move in a circle. So the tension is serving as the centripetal force. Okay, we cannot say that the stone is subject to a tension plus a centripetal force. That wouldn't make any sense, because the tension is what gives you the centripetal force. Okay, the tension provides you with the centripetal force. So let's be careful about that. Okay, from now on, we're going to look at a number of examples on how to apply the dynamical equation for circular motion. Let's see, here is our first example. Suppose you go to one of those amusement park rides, you know, you go a vertical loop-de-loop, okay? This is where you're upside down, the most exciting moment. And you're going in a circle like this, of radius r. So at this one particular moment, you're going with this velocity v, horizontal. You're upside down. You're going in a circle, therefore, somebody has to give you a centripetal force. Okay, so who's doing that? Well, of course, you're upside down. Gravity is always downward, and since you happen to be at the top of the vertical circle, at that moment, gravity happens to be perpendicular to the direction of motion, pointing to the center of the circle. Okay, it only happens at this moment. So gravity, in fact, is serving as part of the necessary centripetal force. So mg, that's one, the gravitational force. Of course, apart from that, you can also have, you know, a force from the track. Okay, if you go really fast, imagine you go really fast, v is so large, you need a large centripetal acceleration because it's proportional to v squared, right? So gravity alone may not be enough. You need a greater force along with gravity to provide you with that centripetal acceleration. So maybe there's another force, n. That n is from the track pushing on the cart. Okay, n and mg are both going downwards, perpendicular to the direction of motion. They're both pointing to the center of the circle. So you add them together, okay? You add mg and n together. That is the centripetal force. Okay, those forces combined serves as a centripetal force, and that provides you with a centripetal acceleration, of course. So that's mv squared over r. R is the radius of the circle. Okay, r is the radius of the circle. And then from that, you can calculate n. Okay, you see, again, if v is very large, that requires a large n because mg is fixed. Now, imagine that you don't go that fast, okay? You're not going all that fast, so that v is not very large. That means only a very small n is required. The track does not have to push the cart very, very strongly. But imagine you go even slower, and even slower, and even slower, okay? At some point you're going so slow that v is so small that n is the smallest possible value. And what would that be? Well, that would be 0, okay? I'm assuming that, you know, the track can only push it, it cannot pull it. So that the worst you can do to n is set it to equal to 0. Okay, that means this side, the left-hand side, has reached the smallest possible value, which is mg. You know, mg cannot change, right? N is now the smallest value, which is 0. Since the left-hand side equals the right-hand side, if the left-hand side is 0, the right-hand side is also 0, which means v is at its minimum possible value. Let's look at what that is equal to. Okay, you have mg equals m v minimum squared over r. What's the meaning of that v minimum? Well, that is the minimum speed that is required for you to clear that highest point in a vertical circle. If v is smaller than v minimum, then no matter what happens to n, even if you set n equal to 0, the right-hand side is still too small compared with the left-hand side, which means the equation is no longer valid, which means you're going too slow. You cannot move in a circle anymore. You're going to fall off the track. Okay, so what is the minimum speed required for you to stay on the track when you're at the topmost point? That is v minimum. And let's solve for it, okay? In fact, you know, m and m cancels, you get v minimum equals the square root of gr. Right? Now, g is the acceleration of gravity. So, what did that tell us? It tells us that if you have a large vertical loop, okay, you build one of those very large tracks, then v minimum required is also larger, which means you have to go faster. Okay, so, you know, when you get a larger track, not only does it look more formidable, but actually going faster in order to stay safe. You know, you have to go faster as well, so it gives you more excitement. Let's look at some numbers, shall we? What is a typical radius of a typical amusement park ride? Well, let's say from here to the topmost point, shall we say, oh, I don't know, 100 feet? Does that make sense? It's like 30 meters. Okay, let's just, you know, roughly estimate to be, let's say 30 meters. So R is about 15 meters. Okay, 15 meters. R is 15 and G is about 10, I'm just estimating, so it's 150, right? And we have to take the square root of that, right? That'll give you about 12 meters per second, and then you translate that to kilometers per hour. That's about 44 kilometers per hour. You can divide by 1.6 to get miles per hour. So divided by 1.6, you get about 28 miles per hour. 28 miles per hour. That's the minimum speed you must have at the top. Of course, when you design an amusement park, they don't let you do that, okay? They must leave a lot of safety margins so that you're not going to go at 28 miles per hour. You're going to go considerably faster than that. So you're actually being pushed down by the track and it's not quite equal to 0. Okay, so but that gives you some idea. And if you design something really much bigger than that, let's say, you design something 4 times as big, so that from here to there, instead of 30 meters, it is 120 meters, okay, a really tall one. Then you see, since V minimum is proportional to R goes by a factor of 4. V has to double, okay, there is a square root here, so that you're not going 28, you have to go a minimum of 55 to 56 miles per hour. That's pretty fast. And that's at the top. Actually, when you go down, you're going even faster than that. Okay, so it is indeed pretty exciting. Okay, so that is the example of an amusement park ride. Now, in this case, somebody is doing a vertical circle, and at the very top, when you set n equal to 0, the only force providing you with a centripetal acceleration is the weight, the gravitational force. And that is not just limited to an amusement park ride. In fact, let's look at something much, much bigger than that. Okay? A near-Earth satellite. So what we have here is the Earth. And there's a satellite that hovers right above the atmosphere. It's very close to the surface of the Earth. So it is also doing a circular motion, right? Because it hovers right above the surface of the Earth. It's doing a circular motion. It is doing a circular motion, therefore somebody has to pull it in, the centripetal force, to provide the centripetal force. Otherwise, if there's nobody's pulling it, it's simply going to go off in a straight line, right? It moves in a circle because there has to be a force pulling it. And who's doing that? Yeah, it's the gravitational force, isn't it? And gravity always points toward the center of the Earth. And therefore, since the Earth is pretty much a sphere, when the thing moves in a circle and the force points toward the center of the circle, that force is just in the right direction to give you the centripetal force. So again, here you're using the gravitational force to provide you with a centripetal force, just like the amusement park ride. So we have V, and then we have the gravitational force Fc, which is equal to Fg, okay? Fg is the gravitational force. So we have here Fc equals Fg. Centripetal force is being provided by the gravitational force. And centripetal force equals mv squared over r. R is the radius of the Earth, okay? It's actually, the actual orbital radius. That's what I should put. But the orbital radius differs from the radius of the Earth only by this little distance here, which is altitude of the satellite, which is, maybe a couple of 100 miles, which is not much compared to the radius of the Earth, which is about 4,000 miles. So roughly speaking, we say mv squared over r, r being the radius of the Earth. So that equals the gravitational force exerted on the object. Now, the satellite is not that high above the surface of the Earth, so the acceleration of gravity at the altitude of the satellite is not that different from the value on the surface of the Earth. So we can still say roughly is equal to 9.8 meters per second squared, and so we have mg. Okay, on this side we have mg. Again, you see m and m cancels, and we can solve for v squared over r equals g. For v, then I have v equals the square root of gr. Alright, now take a look at what we got before. See? V minimum equals the square root of gr. R is the radius of the circular motion. We have something very similar here. V equals the square root of gr. It's not v minimum anymore, because this is the only speed you can have, the satellite must have, in order to move in a circle nicely. You cannot go faster or slower than that. If you go faster, you're not going to go in a circle anymore. Rather, you're going to settle into what's called an elliptical orbit. And if you go slower than that, well, too bad. Because if you go slower than that, there is not enough you do not need that much centripetal force because V is smaller than this value, so this side will be less than that side, so mg is too large. Okay, it does not only give you this, centripetal force, there is something left. So what happens? Well, it's pulling it down. Okay, so it's gonna crash. It's gonna crash to the Earth. So in order to stay in a nice circular orbit above the Earth that hovers above the atmosphere, you must be moving at this speed. Okay, now let's look at what the value of the speed is. Okay, this is we didn't make it up. There is only one such speed. You plug in g and r value. So let's see roughly what that equals to. Okay, 9.8 meters per second squared times the radius of the Earth. You remember what that is? Yeah, it's about 6,400 kilometers, or 6.4 times 10 to the 6 meters. Okay, you work this out. Okay, if this is worth 10 instead of 9.8, then 10 times 64, that's a perfect square. 6.4, that's a perfect square. 64, take the square root, that's 8. What's left? 10 to the 6, you take the square root, will be 10 to the 3. So that will give you 8,000. Okay, 8,000 meters per second. Now, of course, it's 9.8, so the answer is a little bit less than that. It's 7.9 kilometers per second instead of 8 kilometers per second. Okay, this is a large speed. It is not 7.9 meters per second. It is 7.9 kilometers per second. Kilometers per second, that is about 5 miles per second. Okay? 5 miles per second. You compare with the speed of sound in air, in the atmosphere, it is about 25 times the speed of sound. It is truly very large. But if a satellite, or any object for that matter, can move at this speed about the center of the Earth, okay, then it's not going to fall. Not because the Earth has stopped attracting it, precisely because the Earth is still attracting it, but with the right amount of force, so that the weight on the object is just equal to the centripetal force needed for it to move in a circle. Okay, so you're using the gravitational force, the weight, to serve as a centripetal force to move in a circle. That's why you don't end up crashing to the surface of the Earth. And that is the required speed. You can also calculate how long it would take for an object moving with this kind of speed to complete this one revolution around the Earth. That's simple enough to do. In fact, what you do is 2 pi r, that's the circumference, right? 2 pi r divided by that v. Right? And you can do that. It turns out to be quite fast. It takes a little bit less than 1.5 hours to finish one revolution around the Earth. Okay, just a little bit less, a little bit under 1.5 hours to accomplish that. That is a near-Earth satellite. Now, of course, the number here is far greater than the number we got for the amusement park ride. I mean, even if you look at, quite tall one from here to there, 120 meters in diameter, you're still looking at only about 55 to 56 miles per hour. Here, looking at about 5 miles per second, right? The numbers are very different, but I don't want to emphasize the difference. I want to emphasize the similarity. Here is a person riding an amusement park, right? Here is a satellite hovering above the atmosphere. It looks like these two things have very little in common, right? But you see, the underlying physics is so incredibly similar. In either case, I'm using the weight or the gravitational force on that object, satellite or the person, to provide that object with the force necessary to do a circular motion. It's the same exact physical idea. And you get, in fact, the same exact equation. Okay, g times r. The only difference is that the satellite has to move in a much, much bigger circle. Okay, much, much bigger circle, and therefore v has to be much, much greater, because v goes like square root of r. That is the only difference. Okay, so that's what the beauty of physics is. You can relate certain seemingly totally unrelated phenomena, such as the motion of a satellite and amusement park ride, with the same exact physics. So even though they look very different on the surface, underneath they're governed by the exact same laws of physics. That is the beauty of physics.